What's up? This is Matt Brown, and in today's video we are going to continue our series on hacking the Netgear NightHawk router. In this video we are going to be writing a backdoor for this device, inserting it onto the device and demonstrating, for educational purposes, mind you, how an attacker in a supply chain context or in a secondary market context could modify a router like this and maintain persistent access to the device unknowing to the user of the router. And so to do that, we are first going to jump over to our screen. Obviously, we've already gotten that root shell on this device so that we can analyze it to our heart's content and modify the device. If you haven't seen the first video in the series, definitely recommend you check that out. But we're going to head to our computer here, and we're going to start discussing a very basic, we're not going to get too advanced today about trying to hide our network traffic or anything like that. We're just going to demonstrate a very basic backdoor executable that we will eventually be able to load onto this device, that if it was given away, if it was sold to if it was given to Goodwill and then sold to another individual, an attacker could potentially maintain a connection and receive a shell to that device when it is on a victim's network. So to start out here, I have a very simple C program that we have crafted. So we're going to show the source code here. And so what this is going to do, it has hard-coded in this binary a IP and port that is going to connect back. This is the attacker's server. You will notice that this is my desktop's IP address, which is underneath. It's behind my face here. Streaming, but that 10.10.10.2, that is my machine's IP address on my test network here, and so that's hard coded into here. Obviously, if this was a real attack scenario, we would potentially have a domain name that could get resolved, or we would have a public IP hard coded into that location. Then I'm not going to go over this code line by line, but we set up a socket that represents that IP and that port, and then we continuously try to connect up to that host and port. And then once we do, we basically pass off the socket to an exec call. It's going to exec bin.sh, which is the shell on the system. So here in our shell environment, it's just going to be like this root shell here. In fact, I assume if we echo the shell variable, it will give us bin.sh. So that is the shell in this system. So that's good, and that is that's what we're going to execute, and it's going to be connecting back. So this is a reverse shell. It's going to reverse connect out to this system, where we will run netcat or some listener to catch the shell, and then we can execute commands on this remote system. So to quickly demonstrate this, first what we're going to do is we're just going to compile this and show this how this program works on my machine. Then we're going to talk about what it takes to get it onto the router. So to compile a program like this, pretty standard. So we're going to say what we want to write this out as. And so I'm going to just say, I'm just going to call this rev shell. So that's what it's going to be outputted as. And then we're going to compile that C program called rev shell. So when I do that, it compiles just fine. And now I have this program that I can run, and then over in another window, I can maybe run netcat, and I can listen on port 1234, and then we get a connection from the, oh my gosh, the router's connecting to me. Well, that worked too well. My demo worked too well. Okay, we're going to reboot that. Ignore that. So, and then we got a connection here, and you'll notice that this is just my system here. And so in our shell, that we can run that command. That's my user nmat. And you can see that we have like a fully interactive shell on the remote system. In this case, it's the very same system that I'm on in the first place. But you can see that if it were a remote system, then I would have access to that remote system. Now, how do we compile this binary for this device? This binary is not going to work because, let's close out of this. So if we run the file command on all of these files here, we will see that this rev shell program that we compiled is a 64-bit program for the x86-64 system. So this device is not an x86 CPU. Oh gosh, I have to wait for it to reboot. So this is an ARM system, an ARM-based system, and so what we're going to have to do is we're going to have to cross-compile this program. And so this is very useful, not just for backdoors when you're doing IoT pen testing, but also for utilities. In a previous video, we discussed statically compiled versions of Netcat, of the DD program. These are all super helpful for when you don't have a utility on an IoT device and you need to get that utility onto the device. It's typically advisable to statically compile because you're going to have a bunch of problems linking to the libraries on the system because you do not have the SDK, you do not have all the header files that one might need to compile against that system, so it's usually advisable to statically compile for the target system. But even then we can run into some problems, so we're going to let this device boot up, and once it does, we're going to show some issues with this. So I spent a lot of time trying to get a working tool chain that would cross-compile and would work on this target system. And here is one such failed binary. So I found a ARM tool chain, and I was able to statically cross-compile it. So you'll notice that if you run the file program on this test1 ARM, so this is just the rev shell code, but there's something in here that is that from this output that should tell me that we have a problem. But I'm gonna actually load this file onto the device, and we're gonna see what happens when we try to run this, because all of this looks great. 32-bit ARM, that is all correct. But even then, you can still have some problems. So what I'm gonna do is I actually have Nginx running on my computer, and I'm going to pull a file from, I'm going to put this file in the web root so that I can use that web server to serve the file up to the router. And so I'm going to just copy this test1 ARM binary to var www.html, which is my web root. And so now, when I'm over here on the device, I'm going to just go to the temp directory, and I'm going to run wget http 10.10.10.1, so that's my computer, slash, and then I forgot what the file name is. So here we go, test1 ARM. Okay, we got the program. We'll make it executable. There we go. And test1 ARM, when we run it, fatal, kernel too old. So if we look at this system here, we can see that the Linux kernel is ancient. This is quite usual for IoT devices, that you will see decades-old kernels running on modern IoT devices. And so here we have kernel version 2.6. something that is really old. Somebody can correct me in the comments, but I feel like that's more than 10 years old. And so yeah, very ancient stuff we're dealing with. Obviously, like there's some parts of it that are newer. Maybe this is a long-term release, and I could eat my words, but that is a very old kernel version. And if we go back to our desktop system and we look back at this, we can see that this was built against the Linux kernel 3.2. So that's why we're getting that error saying the kernel is just like too old. We don't support that with this statically compiled program. So this led me down a guessing and checking wild goose chase for a tool chain that would work. And so I'm going to show you how I did that and which one finally worked. So if we go over here, we can see, yeah, so this tool chain did work, but I'm going to show you how I found this. So Linaro is a company that releases a bunch of cross-compiling tool chains for all kinds of architectures for embedded devices. Extremely helpful. And they have this archive of all their past tool chains, which is, again, is helpful if you're trying to compile something and get it to work on a really old device. And so what I did here is I just went to the kind of this part of their archive, and here we can see all their versions. And I went back and then I just started kind of going back as far as I could, and I found that this, you know, version 12.01, this tool chain ended up working. So what I'm going to do is I'm going to grab this tool chain here, and we're going to wget that into our tool chain directory. Okay, and so now we're going to uncompress that file. And so now we get this big old thing with a bunch of stuff in it. But I will show you what the important part is. So now we can compile our RevShell C program, but we can do it using the GCC. So before we used the GCC that compiles for a x86 system, but now we're going to use the tool chain that's going to compile it for ARM. And so we're going to go into here, and then all these tool chains pretty much are going to have a bin directory that looks like that. And then all of the tools that you expect for compiling software are going to be prefixed by the architecture, and then the system OS, and then the API, like the library API or whatever. So here it's ARM, Linux, GNU, EABI, and then we have GCC. But you can see, like, you have like G++ for your C++ compiler, but we want GCC. And we're going to say out, we're going to say RevShell ARM. So this is going to be our ARM-based reverse shell backdoor. And then we're going to say -static, right? Because we want to statically compile in all the libraries and put all the stuff it needs and make sure there's no like external library dependencies that it needs. We want it to pack that all into one binary. Again, this makes it a little more portable when you're dealing with embedded systems that you don't know exactly what tool chain they used. Then we're going to specify the RevShell.c program, and we should be good to go. And there we go. So now we have a RevShell ARM binary, and we can run that file command again, and we can see that now we have, like before, we have a 32-bit, least significant bit. That's what we want. ARM, that's what we want. But now this part looks good. Now we have it compiled for GNU Linux 2.6.16, right? It's for 2.6. It's in the right ballpark, right? And this is older, so we shouldn't get that error, you know, kernel too old, right? So now we're going to pop this RevShell ARM program over to that web root. HTML. That will allow us to download it to here. We have it. We're going to make it executable. And now let's get I guess we can do it right here. Get a listener ready with netcat on port 1, 2, 3, 4. Then we're going to run this program, and we can see that it works. Awesome. So we have now this binary that will execute and will give us a shell on the system. But this isn't a backdoor yet, right? Because I'm manually executing this program using the UR shell, which you couldn't do if you had shipped the device off to somebody else, right? So we need to make this program somehow run on boot. Now, normally, on a Linux system, this would be easy, right? I have root on this system. You would think, oh, this is gonna be a cakewalk. Okay, we're gonna close out of that. But the problem is, if we remember from our previous videos, that the main part of this device, the main root file system, is read only. I can't modify anything that's mounted onto slash. And that includes where you would normally put some of the startup stuff, like in etc initd, right? Like I could modify some of these shell scripts that are initialization scripts for this system. Or any number of binaries. I could replace a binary that gets called when the system starts, and that would trigger my backdoor. So here we have to be a little bit more creative because we can't replace any of the common things. So we want to look in the places that we can write. And so that is going to be these places here. So OpenVPN, at least right now, I don't have it configured to run. So we're gonna nix that as an option. We can go look over here into this directory structure, and here there are actually a number of good candidates. So we can just look through a number of these things here for Bitdefender. I know Bitdefender, this is a program that runs when I see a bunch of output in the UART console that is related to this Bitdefender thing. So potentially this BD program will execute at some point. But there's one that I've also seen that I think I have a better shot at backdooring. And that is over in this router analytics. So this AWS JSON program, I've seen specific output that is from this program that prints out roughly when the system, a little bit after the system boots up. This program will get executed. So what I'm going to do, and this is writable, this is great. So something in the main part of the system is calling and executing this binary at some point in that boot up process. So what we're going to do is we're going to move. So first of all, I'm just going to move this out of the way. I don't know why the system started pinging something. Oh gosh, yeah, here you can see it. It's doing something. What a coincidence. Okay, so I'm going to move it out of the way right now. So I'm going to call it just like backup. So we'll move that out of the way. We're not going to delete it just in case the system does need it. I can replace it later. But now we're going to move that temp rev shell arm, and we're going to move it right here, and we're going to call it AWS JSON. So now our reverse shell is the AWS JSON program. And so now all we need to do is set up that listener again, and we're going to reboot because the reboot takes a little while on the system. So I can do that and then get this shell ready. And we will listen, and now we're gonna wait like a whole minute for this system to boot up. So this part of the boot up process, this seems like this should not be happening. It seems like it is checking over the local like a local static IP over the Ethernet interface to load a firmware file, which should be a development feature and should be limited to development firmware. So that's like a potentially risky thing. I don't want to call it a vulnerability, but it's just a risk that they're taking by including this feature in a production device build, in the production firmware. So, and it also slows down the boot time of the device because it waits like a good 15 seconds at that part of the screen. But yeah. So now we have to wait even longer for it to, like, you know, decompress the kernel and to actually start up the system. So now we wait. The suspense of writing malware. Again, this is for educational purposes. I do not condone backdooring a router like this, but this goes to show that when you leave an open, like completely unauthenticated UART console open on a device like this, it would make it really easy for someone to take a device like this, really quickly put in their backdoor, package it back up, and resell and you know, resell that thing on the used market, or try to sell it as new, right? If they can get all the packaging back together just fine. If they return the device back to the store and then it gets put back into good packaging, you never know how that could fall into the victim's hands after it gets modified. All right, so we're starting to get to the initial parts of the boot up process. It should happen sometime here when we get our shell, but you never know. This UART console is also extremely verbose. It's actually kind of crazy how verbose it is. All right, so it really wants me to hit enter here. All right. All right, I'm going to take the bait. I'm going to hit enter. That doesn't actually really change anything. All right, so it's doing some stuff. All right, should happen soon. I'm pretty sure we put our backdoor in there correctly. Hey, we got it. All right, so there we go. We got our shell. Who are we? We're root. Awesome. We backdoored this router. So, it doesn't have to just be building a backdoor program like this. Again, there are often times where it is extremely helpful. We've talked about doing network analysis in other videos where we're doing that over the network, but there are some situations where it's extremely helpful to get TCP dump loaded onto a device and run it on the very device. In the case where maybe the device is running a VPN and you really can't get in the middle of that VPN tunnel, but you could listen on the device to clear text traffic after it comes out the other end of a VPN tunnel, or before it goes in a VPN tunnel. Those are all options that are available to you if you can statically compile programs to get them on a system like this. But thank you for watching this video. I would encourage you to leave a comment, tell me what you think, tell me what other type of content you would like me to be covering in future videos, and I'm going to plug it again, but most likely on Friday I will drop a video that will include the details to a Discord server, which is going to be the beginning of a IoT hacking community that we can all get together and talk about the hardware hacking, IoT hacking projects that we're working on, and share knowledge and just have a good time together. So be on the lookout for that. And that's all I got for you. Thank you and have a good day.